In this section of Chapter 2, we're going to discuss some of the early ideas in atomic theory. Specifically, we're going to look at Dalton's model for the atom, and we'll also look at some of the experiments that actually confirmed his hypothesis about the atom. In the early 1800s, John Dalton did a significant number of experiments on different types of matter, and he came up with a model for the atom. He said that matter was made up of tiny spheres that were able to bounce around with perfect elasticity, and he called them atoms also. He actually had a periodic chart which had 8 different atoms in it. For example, if I look at copper, copper is made up of little tiny spheres of copper, and he represented those as sort of a circle with the letter C on them. There are 5 postulates that Dalton made about the atom. Dalton's first postulate is that matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical reaction. In other words, you cannot break down an atom any further. For example, I have copper atoms and I have oxygen atoms. His second postulate is that an atom consists of only one type of atom, which has a mass that is characteristic of that element. So for example, oxygen has a certain mass, and copper has a certain mass, and each element is only that element. It's the same atoms for that element. His third postulate is that atoms of one element differ in properties from atoms of all the other elements. For example, copper is a brown solid, and oxygen is a colorless gas. His fourth and fifth postulates are: a compound consists of atoms of 2 or more elements combined in small whole number ratios, meaning if I have one copper atom, it has to combine with 1 or 2 or 3 or 4 oxygen atoms. It can't combine with 1.5 oxygen atoms. So in a given compound, the number of atoms for each of its elements are always present in the same ratio. His fifth postulate is that atoms are neither created nor destroyed in a chemical change, but instead rearranged to yield a different type of matter. In the example shown here, one copper atom combines with 2 oxygen atoms to form a new compound, which we're going to find out later is copper 2 oxide, and it always combines in that same ratio. There are some experiments that confirmed Dalton's atomic model, and they're historical experiments. Even before Dalton, several experiments were done which showed Dalton's theory of the atom was a good start. One of them was the law of conservation of mass, which actually was developed by Lavoisier in the early 1700s. His law stated that during a chemical or physical change, matter is neither created nor destroyed. The experiment that he used was actually the decomposition of mercuric oxide. That's shown here in these spheres of mercury and oxygen. He heated up a sample of mercuric oxide in a test tube, and he saw that there was a gas formed and there was a liquid formed, both mercury and oxygen. So by taking mercuric oxide, he gets mercury and oxygen. And he meticulously did a number of these experiments where he used a balance. In fact, he was the first person documented to use a balance in chemistry. So what his postulate said was that if atoms are neither created nor destroyed during a chemical reaction, then the total mass that is present when matter changes from one type to another should remain constant. So If you would take 100 grams of mercuric oxide, heat them up in a test tube, he found that he get 92.61 grams of mercury and 7.39 grams of oxygen. Together, these equal 100 grams. Another law before Dalton is the law of definite proportions, which states a compound always contains the same elements in certain definite proportions. This law was first proposed by Proust in 1799. One of his experiments showed that regardless of the source, compounds like copper carbonate always have the same composition, whether they're in a rock, whether they're in a gem, or whether they're on the roof of a building. It always contained 57.48% copper, 5.43% carbon, 0.91% hydrogen, and 36.18% oxygen. Another scientist, Berzelius, took that one step further, where he did some experiments to prove the law of definite proportions. In his case, he took 100 grams of lead and 1.55 grams of sulfur, and he actually formed 11.55 grams of lead sulfide. And he did this experiment hundreds and hundreds of times. What he did next is he took that 10 grams of lead and he took extra sulfur. What he found out is he still created just 11.55 grams of lead sulfide, but he was left over with 1.45 grams of sulfur that did not react. What that said was that both lead and sulfur only combine in definite proportions to make so much lead sulfide. He did the same experiment taking excess lead this time and the same amount of sulfur, and he still only produced 11.55 grams of lead sulfide. In this case, he had 8.00 grams of lead left over. Experiments that illustrated the law of definite proportions. John Dalton expanded on the law of definite proportions and proposed the law of multiple proportions. What he found was that elements can combine in different ways to form different chemical compounds. However, they always combined where the mass ratios are simple whole number multiples of each other. His experiments included reacting nitrogen with oxygen. In some cases, when he did that chemical reaction, he found out that for every gram of oxygen he used, he formed 1.75 grams of nitrogen. In other cases, if he used 1 gram of nitrogen, he only used 0.875 grams of nitrogen. And in the third case, he only used 0.4375 grams of nitrogen. And he measured the physical properties of these three compounds, and they were different compounds. Doing a little simple math, what he found out is that they are all whole number ratios of each other. What that implies is that we know now that if I have one atom of oxygen, it can react with 2 atoms of nitrogen, or 1 atom of nitrogen, 1 atom of oxygen, 2 atoms of oxygen, and 1 atom of nitrogen. Law of multiple proportions. How does one explain these properties? Because it must be more than just small balls bumping into each other, and that's what we're going to look at in the next section.